So that brings us to atomic spectroscopy. When atoms or molecules absorb energy, that energy is often released as light. And examples of this are fireworks and neon lights. So these are three different elements, mercury, helium, and hydrogen. And these lamps are the same principle as neon lights, like this. So this light is a tube of gas, of neon gas, and you pass electric current through it, and it glows bright orange. It's not because the glass is orange. The gas makes that bright orange color, and we'll see that in lab in about a week or two. So this is what mercury does. It gives off this bluish light. Helium gives off sort of a purple light, and this is more of a pinkish red light when you're passing electric current through hydrogen. So different elements give us different colors, and so all the different colors you see in fireworks are because they put different elements in the explosives. Blue is one of the hardest ones for them to get. So if we take that light that's emitted by an element or a molecule, we don't get a rainbow of light if we pass that through the prism. We see a series of lines, basically, bright lines. It's not continuous. It's almost like a fingerprint or a barcode. It is specific to that element. Doesn't matter where you got the element from, mercury will always give you the same barcode, right? And this cannot be explained by classical physics. So this is what's going on here. So here we have a hydrogen lamp, and its light is going through a slit just to focus it, and then it's going through a prism where it's going to get separated into a rainbow, except there's only 3 colors in there instead of a continuous varying band of colors. If you do it with helium, you get something like this. Barium would give you this. It's got more lines. And white light, such as from the sun, here you'd see the rainbow. This is oxygen and neon. So this is emission spectroscopy, where we're looking at the spectra that is released, energy being released. You can also look at what light energy is being absorbed, and it will have dark spots in the same place if you're looking at absorption of energy. So identifying elements with flame tests is a very, very old technique. Sodium gives a very bright yellow, orangish light. Potassium's green. Lithium is this beautiful red color, and barium has this really faint greenish color. And so, you can put different elements in a flame, and the color of the flame can tell you what the element is. So seeing all those things is really cool, but then scientists are like, well, what about those lines? Why are they these particular wavelengths? Well, a guy named Johannes Rydberg analyzed lots and lots of atomic spectra, and he found that they could be described using an equation, and this is the equation he came up with. 1 over the wavelength is equal to a constant times 1 over m squared minus 1 over n squared. M and n are just integers. But like if you put 1 and 2 in there, you can calculate a wavelength, and that is a wavelength that one of the elements gives off. Will be one of the light bars. It doesn't say anything about why or how this happens. So, yay for you, you made this equation, but it's not really telling us what's going on. So, we talked about Rutherford's nuclear model of the atom that came after the blueberry muffin model, the plum pudding model. So here we have the atom with a dense center called the nucleus. The nucleus contains essentially all the mass of the atom. It's positively charged, and then we have electrons moving around in empty space nearby. And the number of electrons is equal to the charge on the nucleus. Well, electrons are moving charged particles, and according to classical physics, a moving charged particle gives off energy. So then electrons should be constantly giving off energy, then atoms should glow because they're giving off energy all the time. But the other thing that means is that the electrons are losing energy. Where are they getting the energy from? They're just losing energy. They're going to collapse into the nucleus. But that doesn't happen. So classical physics just does not explain what happens. And the nuclear model also gives us no insight into what happens when atoms gain or lose energy. So we just saw these lamps. You pass electric current through mercury gas, and it glows. It gives off light. What's causing that? So a guy named Niels Bohr, the same one with the quote at the beginning of the chapter, he developed a model of the atom that explained what happens inside the atom when it undergoes energy transitions. And his model is much easier to understand than some of the other models. In his model, the electrons are traveling around the nucleus in circular orbits, a lot like the planets travel around the sun, right? So the Earth goes around the sun, and you can predict where it's going to go, right? So the orbits here are at specific fixed distances from the nucleus. Like, there's Earth and Mercury, Mars, right? There aren't like options in between. There's only these set patterns, set paths. So the energy of each of those orbits is also fixed. It's related to the distance from the nucleus, and we say that's quantized. So quantized means there's only certain levels that are available. So we have quantized things in everyday life. Our monetary system is quantized. So if you think about coins, there's a 1 cent and 5 cents and 10 cents and 25 cents, right? Anybody ever seen a 13-cent coin? No, they don't exist. If you want 13 cents, you'll take a dime and 3 pennies, right? There's nothing in between. School, K-12 is like that. You're in first grade or you're in second grade. Walking up steps. I don't think I have a picture here. I think I always have to draw the picture. Just want to make sure we understand what quantized means. So if you're walking upstairs, there's supposed to be more down there. You can stand on the first step or the second step or the third step. You can't stand in between. Same thing with climbing up a ladder, right? There's rungs, and you can't stand in between. Whereas if you have a ramp, you could be at any place, at any elevation above the ground. This is not quantized. This is a continuous situation. These are quantized. There's only particular levels that are possible. So imagine that these circles, keep going around. They're not half circles. So here's the nucleus, and here's the first level, the second level, the third, the fourth, and the fifth. So these are the orbits that are possible for electrons. And what happens when an atom absorbs energy is that an electron will go from a lower energy level to a higher energy level when it absorbs the energy. But it's not stable, and so eventually it'll fall back down, and when it falls back down, it releases energy that's equal to the difference between those two energy levels. And for some of those transitions, it's visible light. We can measure the wavelength and determine the energy difference between the different levels. So what hydrogen is doing with its 3 lines, that violet light corresponds to an electron going from the 5th level to the 2nd level. The blue-green one is from 4 to 2, and the red one is from 3 to 2. There are no lines in between here because there's no place between n equals 3 and n equals 4 for an electron to be. So you can't have a different transition. Those are the only transitions that are possible right there. So from the wavelengths of the light, we can find the difference in energy for the orbits. The electrons are never between states. So let's go back to this. So the electron was here, and then it's over there. It doesn't move through space to do that. It was here at this energy, and then bam, it's here at this energy. Yeah, narrowed eyes, that's the, what? Okay, you know the TV show Quantum Leap? They have a new version out. It's kind of neat. So the guy leaps, right? He goes from being in this one place in time to being in some other place and some other time. Does he travel through space in between? No. It's a quantum leap. It's from one place to the other without going in between. We don't have to understand it. It's okay. Ooh, cool. So the quantum leap is a real thing, except that people can't do it, actually. But electrons do. So the energy that photon emits is the energy difference between those two states, and we can calculate the difference in energy. So that is all really wonderful and everything. The issue is that the Bohr model only works for hydrogen. Hydrogen has 1 electron. It works great for hydrogen. Has great historical importance. And I think it's also helpful because it's a simpler way to think about the structure of the atom, just as a starting point. But it was replaced by the quantum mechanical